Welcome friends to a new session on differential geometry. In this chapter, we will see various topics in Riemannian geometry. Elements of Riemannian geometry Part 1. In the early 1800s, Gauss asked how much of the geometry of a surface is independent of how it bends in space. Riemannian geometry is designed to describe the universe of creatures who live on a curved surface and who are unaware of space outside and can only measure distances and areas on the surface. This led to the modern notion of a manifold independent of a surrounding space. Let us start with some basic definitions. Module 1. Manifolds and differentiable manifolds. A topological space is a set capital M together with a family O of subsets of M satisfying the following properties. First one, omega 1 omega 2 element of O implies omega 1 intersection omega 2 is an element of O. Second one, for any index set A, omega alpha where alpha element of A is a subset of O implies union alpha element of A, omega alpha is an element of A. And third one, the empty set and the whole set M is an element of O. The sets from O are called open. A topological space is called Hausdorff if for any two distinct points P1 and P2 element of M, there exist open sets omega 1 and omega 2 element of O with P1 element of omega 1 and P2 element of omega 2 and omega 1 intersection omega 2 is empty set. A covering omega alpha element of A, where A is an arbitrary index set, is called locally finite if each P element of M has a neighborhood that intersects only finitely many omega alpha. M is called paracompact if any open covering possesses a locally finite refinement. This means that for any open covering omega alpha where alpha belongs to A, there exists a locally finite open covering omega dash beta where beta element of A with for all beta element of B, there exists an alpha in A such that omega dash beta is a subset of omega alpha. A map between topological spaces is called continuous if the pre-image of any open set is again open. A bijective map which is continuous in both directions is called a homeomorphism. After understanding these basic terms from topology, let us now go ahead and define a manifold. Definition 1. A manifold capital M of dimension D is a connected paracompact Hausdorff space for which every point has a neighborhood capital U that is homeomorphic to an open set omega subset of Rd. Such a homeomorphism X from U to omega is called a coordinate or a chart. An atlas is a family set U alpha X alpha of charts for which the U alpha constitute an open covering of capital M. A point P belongs to U alpha is determined by X alpha P, hence it is often identified with X alpha P. Often also the index alpha is omitted and the components of XP element of Rd are called local coordinates of P. Any atlas is contained in a maximal one, namely the one consisting of all charts compatible with the original one. Definition 2. An atlas U alpha X alpha on a manifold is called differentiable if all chart transitions X beta composite X alpha inverse such that X alpha U alpha intersection U beta goes to X beta U alpha intersection U beta are differentiable of class C infinity in case U alpha intersection U beta is an empty set. A maximal differentiable atlas is called a differentiable structure, and a differentiable manifold of dimension D is a manifold of dimension D with a differentiable structure. From now on, all atlases are supposed to be differentiable. Two atlases are called compatible if their union is again an atlas. In general, a chart is called compatible with an atlas if adding the chart to the atlas yields again an atlas. An atlas is called maximal if any chart compatible with it is already contained in it. Note 1. Since the inverse of X beta composite X alpha inverse is X alpha composite X beta inverse, chart transitions are differentiable in both directions. that is diffeomorphisms. Second one could also require a weaker differentiability property than C infinity. Third one, it is easy to show that the dimension of a differentiable manifold is uniquely determined. For a general not differentiable manifold, that is much harder. Fourth one, since any differentiable atlas is contained in a maximal differentiable one, it suffices to exhibit some differentiable atlas if one wants to construct a differentiable manifold. The figure 1 shows a local coordinate system XU on a manifold M. We will move on to next definition. An atlas for a differentiable manifold is called oriented if all chart transitions have positive functional determinant. A differentiable manifold is called orientable if it possesses an oriented atlas. It is customary to write the Euclidean coordinates of RD, omega subset of RD open as x is equal to x1, x2, etc. xd, and these then are considered as local coordinates on a manifold capital M when x from u to omega is a chart. Examples. First one, the sphere Sn, which is a set x1, x2, etc. xn plus 1 element of Rn plus 1 such that summation I equal to n plus 1 xi square is equal to 1 is a differentiable manifold of dimension n. Charts can be given as follows. On u1 is equal to Sn minus set 0 0 0 0 1, we put f1 of x1, x2, etc. xn plus 1 is equal to f1 1 x1, x2, etc. xn plus 1 etc. f1 n x1, x2, etc. xn plus 1, which is equal to x1 by 1 plus x raised to n plus 1 etc. etc. x raised to n by 1 plus x raised to n plus 1. Example 2. Let w1, w2, etc. wn element of Rn be linearly independent. We consider z1, z2 element of Rn as equivalent if there are m1, m2, etc. mn element of z with z1 minus z2 is equal to the summation I equal to 1 to n mi wi. Let pi be the projection mapping z element of Rn to its equivalent class. The torus Tn is equal to pi of Rn can then be made a differentiable manifold of dimension n as follows. Suppose delta alpha is open and does not contain any pair of equivalent points. We put u alpha is equal to pi of delta alpha. Z alpha is equal to pi given delta alpha inverse. Third one, the preceding examples are compact. Of course, there exist also non-compact manifolds. The simplest example is RD. In general, any open subset of a differentiable manifold is again a differentiable manifold. Fourth example, if capital M and n are differentiable manifolds, the Cartesian product M cross n also naturally carries the structure of a differentiable manifold. Namely, if u alpha x alpha were alpha element of A and v beta y beta where beta is an element of B are atlases for M and n respectively, then u alpha cross v beta x alpha y beta for alpha beta element of A cross B is an atlas for M cross n with differentiable chart transitions. Next definition, a map H from M to M dash between differentiable manifolds M and M dash with charts u alpha x alpha and u alpha dash x alpha dash is called differentiable if all maps x beta dash composite H composite x alpha inverse are differentiable of class C infinity as always were defined. Such a map is called a diffeomorphism if bijective and differentiable in both directions. For purposes of differentiation, a differentiable manifold locally has the structure of Euclidean space. Thus, the differentiability of a map can be tested in local coordinates. The diffeomorphism requirement for the chart transitions then guarantees that differentiability defined in this manner is a consistent notion, that is independent of the choice of a chart. Next definition, a complex manifold of complex dimension D is a differentiable manifold of real dimension 2D whose charts take values in open subsets of CD with holomorphic chart transitions. In the case of a complex manifold, it is customary to write the coordinates of CD as z is equal to z1, z2, etc. zd with zj is equal to xj plus iyj with I equal to root of minus 1, that is use x1, y1 etc. xd, yd as Euclidean coordinates on R2D. We then also put xj bar is equal to xj minus iyj. The requirement that the chart transition z beta composite z alpha inverse from z alpha u alpha intersection u beta to z beta u alpha intersection u beta be holomorphic, then is expressed as dou z beta j by dou z alpha k is equal to 0 for all j comma k, where dou by dou z k is equal to half of dou by dou x k plus I dou by dou y k. We also observe that a complex manifold is always orientable because holomorphic maps always have a positive functional determinant. Tangent space. Let x equal to x1, x2 etc. xd be Euclidean coordinates of Rd open and x dot element of omega. The tangent space of omega at the points x0, t x0 omega is the space set x0 cross E, where E is the d-dimensional vector space spanned by the basis dou by dou x1 etc. dou by dou xd. Here dou by dou x1 etc. dou by dou xd are the partial derivatives at the point x0. If omega is a subset of Rd, omega dash is a subset of Rc are open and f from omega to omega dash is differentiable, we define the derivative df of x dot for x dot element of omega as the induced linear map between the tangent spaces df x dot from t x naught omega to t f x naught omega dash. V is equal to Vi dou by dou xi goes to Vi dou fj by dou xi at x dot dou by dou fj. Here Vi dou by dou xi is an abbreviation for summation I equal to 1 to d Vi dou by dou xi, and Vi dou fj by dou xi x dot dou by dou fj stands for summation I equal to 1 to d summation j equal to 1 to c Vi dou fj by dou xi dou by dou fj. Thus we have t omega which is equal to omega cross E, which is equivalent to omega cross Rd. Thus t omega is an open subset of Rd cross Rd, hence in particular a differentiable manifold. Pi from t omega to omega, that is a projection into the first factor where xv goes to x, is called a tangent bundle of omega. T omega is called the total space of the tangent bundle. Next is submanifolds. A differentiable map f from M to N is called an immersion if for any x element of capital M, df from Txm to Tfxn is injective. In particular, in this case M is the dimension of capital M which is less than or equal to N, which is the dimension of N. If an immersion f from M to N maps homeomorphically onto its image in capital N, f is called differentiable embedding. If f from M to N is a differentiable embedding, Fm is called a differentiable submanifold of capital N. Reimannian metrics. We now want to introduce metric structures on differentiable manifolds. Again, we shall start from infinitesimal considerations. We would like to be able to measure the lengths of and angles between tangent vectors. Then one may, for example, obtain the length of a differentiable curve by integration. In a vector space, such a notion of measurement is usually given by a scalar product. Next definition: a Reimannian metric on a differentiable manifold M is given by a scalar product on each tangent space Tpm, which depends smoothly on the base point P. A Reimannian manifold is a differentiable manifold equipped with a Reimannian metric. In order to understand the concept of a Reimannian metric, we again need to study local coordinate representations and the transformation behavior of these expressions. Thus, let x equal to x1, x2 etc. xd be local coordinates. In these coordinates, a metric is represented by a positive definite symmetric matrix Gijx, where ij is equal to 1 to d. That is, Gij is equal to Gji for all ij, and Gij zeta I zeta j is greater than 0 for all zeta is equal to zeta 1 etc. zeta d not equal to 0, where the coefficients depend smoothly on x. The transformation formula given will imply that the smoothness does not depend on the choice of coordinates. Therefore, smooth dependence on the base point as required in the definition of Riemannian metric can be expressed in local coordinates. The product of two tangent vectors v, w element of TPM with coordinate representations v1, v2 etc. vd and w1, w2 etc. wd, that is v is equal to vi dou by dou xi, w is equal to wj dou by dou xj, then is the inner product v w is equal to gij x of p vi wj. In particular, the inner product dou by dou xi dou by dou xj is equal to gij. Similarly, the length of v is given by norm v is equal to the inner product vv raised to half. We now want to study the transformation behavior. Let y equal to fx define different local coordinates. In these coordinates, v and w have representations v1 tilde etc. vd tilde and w1 tilde etc. wd tilde, with vj tilde is equal to vi dou fj by dou xi and wj is equal to wi tilde dou fj by dou xi. Let the metric in the new coordinates be given by hkl of y. It follows that hkl of f of x vk tilde wl tilde is equal to the inner product vw, which is equal to gij of x vi wj. Hence, hkl of f of x dou fk by dou xi dou fl by dou xj vi wj is equal to gij of x vi wj. And since this holds for all tangent vectors v, w, hkl of fx dou fk by dou xi dou fl by dou xj vi wj is equal to gij of x, and this formula gives the transformation behavior of a metric under coordinate changes. The simplest example of a Riemannian metric, of course, is the Euclidean one. For v equal to v1, v2 etc. vd and w is equal to w1, w2 etc. wd, element of Tx of Rd, the Euclidean scalar product is simply delta ij vi wj, which is equal to vi wi, where delta ij is equal to 1 for I equal to j and 0 for I not equal to j is the standard Kronecker symbol. Let us see a theorem now. Theorem: each differentiable manifold may be equipped with the Riemannian metric. The proof is like this. Let the set x alpha u alpha, where alpha belongs to A, be an atlas, and phi alpha alpha belongs to a partition of the unity subordinate to u alpha alpha element of A. For simplicity of notation, we use the same index set for phi alpha and u alpha. This may be justified by replacing the original covering u alpha by a locally finite refinement. For v, w element of TPM and alpha element of A with p element of u alpha, let the coordinate representations be v alpha 1 etc. v alpha d and w alpha 1 etc. w alpha d. Then we put inner product v w is equal to summation over alpha element of A with p element of u alpha of phi alpha p v alpha I w alpha I. This defines a Riemannian metric, and the metric is simply obtained by piecing the Euclidean metrics of the coordinate images together with the help of a partition of unity. Length and energy of smooth curves. Let closed interval AB be a closed interval in R and gamma from closed interval AB to M a smooth curve, where smooth as always means of class C infinity. The length of gamma then is defined as L of gamma is equal to integral A to B norm d gamma by dt of t dt, and the energy of gamma is E of gamma is equal to half integral A to B norm d gamma by dt of t square dt. In physics, E gamma is usually called the action of gamma, where gamma is considered as the orbit of a mass point. Of course, these expressions can be computed in local coordinates. Working with the coordinates x1 gamma t etc. xd gamma t, we use the abbreviation x dot it is equal to d by dt xi of gamma t. Then L of gamma is equal to integral A to B square root of gij x of gamma t x dot it xj dot t dt. and E of gamma is equal to half integral a to b gij x of gamma t xi dot t xj dot t dt. We can also see that the length of a continuous and piecewise smooth curve may be defined as the sum of the lengths of the smooth pieces, and the same holds for the energy. On a Riemannian manifold capital M, the distance between 2 points P and Q can be defined as d of PQ is equal to the infimum of the set of all L gamma, where gamma from AB to M is piecewise smooth curve with gamma A equal to P and gamma B equal to Q. Any 2 points P and Q in M can be connected by a piecewise smooth curve, and dPQ therefore is always defined. Namely, let EP is a set of all Q in M where P and Q can be connected by a piecewise smooth curve. With the help of local coordinates, we can see that EP is open. But then also M minus EP is equal to union Q not an element of EP of EQ is open. Since M is connected and EP is equal to MT, where P is an element of EP, we conclude M is equal to EP. The distance function satisfies the usual norms, which is written as the following lemma. First one, dPQ is greater than or equal to 0 for all P and Q, and dPQ is equal to 0 for all P equal to Q. Second one, dPQ is equal to dQP, and third one, dPQ is less than or equal to dPr plus dRQ, the triangular inequality for all points P, Q are element of M. A corollary. The topology on M induced by the distance function d coincides with the original manifold topology of M. Proof. It suffices to show that in each chart the topology induced by d coincides with the one of Rd, that is the one induced by the Euclidean distance function. Now, for every x in some chart there exists an epsilon greater than 0 for which d epsilon x is contained in the same chart, and positive constants lambda and mu, lambda into mod zeta square is less than or equal to gij of y into zeta I zeta j is less than or equal to mu into mod zeta square for all y element of d epsilon x and zeta element of Rd. And thus each Euclidean distance ball contains a distance ball for d and vice versa, with Bz delta is equal to the set of all y element of M where dzy is less than or equal to delta. We have d lambda delta dot x is a subset of Bx delta dot subset of d mu delta dot x if mu delta is less than or equal to epsilon. Before concluding the session, let us summarize what we have learned. We have started our chapter on Riemannian geometry with some basic definitions. We have defined the notion of manifolds and submanifolds and seen various examples for it. Then we defined tangent spaces, and we introduced the metric structure on manifolds, which is called the Reimannian metric. We have also seen some results as theorems and lemma on these topics. Now, these are some exercise problems which you can try out for a better understanding of the topic discussed in this session. First one, give 2 more examples of differentiable manifolds besides those discussed in the text. Second one, determine the tangent space of Sn. Give a concrete description of the tangent bundle of Sn as a submanifold of Sn cross Rn plus 1. Third problem, let n be a differentiable manifold where f from m to n is a homeomorphism. Introduce a structure of a differentiable manifold on M such that f becomes a diffeomorphism. Show that such a differentiable structure is unique. Fourth one, can the boundary of a cube, that is the set x element of Rn where maximum xi where I equal to 1 to 3 etc. n is equal to 1 be equipped with the structure of a differentiable manifold. Now, I will suggest some books for further reading. First one is Introduction to Differential Geometry by J. A. Thorpe, Springer Verlag. Second one is Lecture Notes on Elementary Topology and Geometry by I. M. Singer and J. A. Thorpe, Springer Verlag 1967. Third one, Elementary Differential Geometry by B. O. Neal, Academic Press 1966. Fourth one is the Lectures on Differential Geometry by S. Sternberg, Prentice Hall 1964. Fifth one, Differential and Riemannian Geometry by D. Lovitz, Academic Press 1965. Sixth one, Riemannian Geometry by S. Gallard, D. Hullin and J. Lafontaine. Springer Verlag 1987, and the last one is Reimannian Geometry and Geometric Analysis 4th edition by Jürgen Jost Springer. Thank you for watching this session. We will continue with Romanian metric in the next session. Till then, goodbye.